I'd like to welcome everyone who is just watching 8.5.1 to 8.5.2. This is just so cool, I have to share. It has nothing to do with vectors, but I'm sitting here, we had a 2-hour delay in the morning, so I'm like, well, let me get a head start on the next video. And, well, I just checked again, and we are now closed. How exciting is that? So what do we got here? Oh, you gotta love it. So anyway, I'm gonna finish this video. I'm gonna get rid of that, I guess. Just needed a moment of excitement. How can I not share it with everyone? I have a pre-drawn diagram this time. I'd like all of you to just pause this momentarily and get this in your notes before we continue. Alright, so there you have it. Now, what we got here is a 17 Newton force at a 90-degree angle. So there's my 17 Newton force at my 90-degree angle. And we have a 12 Newton force at a 30-degree angle. When it doesn't say, it assumes standard position. Now, because of position, if this is 90 degrees, that means that the vector must be pointing this way, okay? And if they say 30 degrees, well, if that's the direction, that means that at 30, it has to be pointing that way. So I'm going to draw my parallelogram, and this is going to bring, this is just going to be translated over here, and this one I'm just going to translate up over here, which gives me my scenario where I have two forces acting concurrently or at the same time on a point. And what is the magnitude to the nearest tenth and direction to the nearest degree of a third force that produces equilibrium? What's equilibrium? It is when forces balance each other. There's no motion. If I have one force coming this way and this other one coming this way, so long as they're balanced, there's no motion. They're keeping each other still. But if this one's stronger than the other one, you know, like whatever, well, then you're going to have more motion that way. They're not at equilibrium. First, the magnitude. We want to know the magnitude of the equilibrium vector. So the equilibrium vector is this gray one. Actually, I should draw that longer because that's going to ultimately be equivalent or congruent to the resultant vector. And the resultant vector is going to be this one over here. And if they're going to be in equilibrium, whatever the magnitude of this one is, well, then the magnitude of this has to be the same to keep them intact, because this is the net force on that blue point right there. So we find the resultant here, and we have our answer there the same. The only thing you got to consider is the direction. Now, this one is pointing, you know, there's a positive direction going up this way. This one is not. This is coming down this way, which means vectors can be moved anywhere so long as they keep their same length and direction. If I were to translate that, if I were to translate this equilibrium vector so it would start at the origin, like we were talking about in class, it would be going down here. It would be pointing, hang on one second. I'm going to translate this gray vector down here, and it's going to be pointing this way. Okay, so the direction for that one is going to be a big obtuse angle like this. All right, so if you get a big angle answer, you're probably correct. We are going to leave this diagram up over here, so hopefully it'll absorb into your brain at some point. Hopefully it makes sense. Now, we talked about equilibrium. Let's figure it out. So we're going to use law of cosines. And I have x squared. What am I calling x? I'm calling the resultant over here x. I should have written that in before. I don't know. Ask an English teacher. I'm not sure. X squared equals 12 squared plus 17 squared. That's the part that looks like Pythagorean theorem. And all I'm doing is plugging in the appropriate side lengths and angle values, I'm sorry, that's cosine, into the law of cosines formula. Make sure you're in degrees. We have a 120 degree value. You can solve for x, hopefully, and you'll get a value of 25.2. And what are we talking about? Newtons? We have 25.2 newtons. That is the force that we need on the equilibrium vector to attain equilibrium, if you will. Oops, I just realized. I threw in 120 degrees right here, and, well, where did that come from? Let me explain that real quick. Over here in our picture, we have this angle is 60 degrees. That was given to us. Well, not given to us, but we were able to figure it out because of the 90 and the 30. And if that's the case, well, these are supplementary, so that has to add up to 180. So if that's 60, this angle in over here has to be 120. So that's where my 120 came from. Alrighty. Now for the law of sines. Now that we know x is 25.2, right here x is 25.2, and that is what we're trying to find because I guess I should point it over here. This x and this x, that has to be congruent if they're in equilibrium. Technically, this is the x we're finding, though. That's the vector we're focusing on. Anywho, we have 25.2 is to the sine of 120 as what? Well, let's make sure we're using the right side length. In this diagram again, let's just go back here. Okay, what is it we're looking for? Let me just color this in. We can use yellow. We want to find, now we know this piece right here, we're trying to find this big obtuse angle. Well, this piece right here is 30 degrees. And this right here, this is nothing more than a straight line. And straight lines have 180 degrees to it. So this piece of our obtuse angle is 180 degrees. We know that piece of our obtuse angle. We know this piece of our obtuse angle. The only piece of our obtuse angle that we are not sure about is this orange sector right here, if you will. Okay? And that's what we're going to find. So what's the side length across from that? 17. Just make sure you're using the right side length. Okay, hopefully that all makes some sense to you. Back to our law of sines. So we have, so now we're using 17 is to the sine of theta. And that will give us the angle that we're looking for to complete that obtuse angle. You've seen me do it a few times. I'd like to just have you do it again here. If you do it properly, you're going to get theta equals arc sine of, that will come out to be 17 times the sine of 120. And you'll have that divided by 25.2 once you divide both sides by 25.2. And you're in degrees, right? So that's going to give you a value of approximately 25.2. It tells us to round to the nearest tenth up there, so 25.2 newtons. Okay, that right there is the incorrect that right there is the incorrect answer. I just quickly looked at my cheat sheet over here and copied this number down. Ho ho ho, silly me. Anywho, if you plug it in correctly, what you should get is in green over here, 36 degrees. It tells us to round that one to the nearest degree. So 36 degrees is what we get. Now that we have our missing angle of 36 degrees, let's go back to our obtuse angle that we're trying to find, because that is the direction of this equilibrium vector. We now know that this piece right here is 30 degrees. That was, we figured that out. This right here was the missing angle. We just figured that one out to be 36 degrees. This right here is a straight line, which tells us that this angle is 180 degrees. If I take these three angles and add them up, we have our answer. 180 plus 36 plus 30 is going to give you 246 degrees. That is the direction of our vector. That is just some good stuff. Applying vectors in the real world. How can you go wrong? Well, what do we got going here? We did day 6, it looks like, applications with vectors. So expect to come into class the next class day, and we're going to work on page 439. We're going to do those problems. Those are very similar to the 3 we just did together. Okay, so we are going to, get this into the last part of your notes. That's what we're going to work on in class. See you then.